Hi there. Today I'm going to demonstrate a simple way of making a mathematical model to predict the growth of an epidemic. This model is going to be based on the current data that is being made available from the ongoing pandemic of the coronavirus disease. As we know, epidemics are not very common. In fact, most of us hope that we will go through our lifetime before we go through an epidemic. Of course, this has changed now. And when epidemics do happen, because they sometimes do, they are eliminated as quickly as possible before they cause a lot of deaths and a lot of suffering. What this means then is that we never get sufficient time to collect adequate data to test existing mathematical models, or perhaps even to come up with ways of modeling, coming up with new models, because data is everything. The current pandemic is a bit different. It is generating a lot of data, and it is happening at a time when data is readily shared around the world. There are many websites you can scroll through and find day-to-day data, sometimes hour-to-hour data, or hourly data for that matter, on various, what is happening in different countries. Websites such as this, odometers, corona cases in the UK, this is from the BBC for example, and this is another one reporting cases in France, actually given by the different regions of France. So this is giving an unprecedented opportunity to test existing models and at the same time to come up with new approaches to develop our models for determining the growth of such epidemics. If you look at the current pandemic, you can consider it to be like many epidemics happening at the same time. An epidemic in Italy, an epidemic in France, an epidemic in UK, an epidemic in the USA, and soon enough, of course, we'll be having an epidemic in each and every country in the world. So it's possible for you to model using data from one country and also authenticate data from the neighboring country. Of course, we don't hope that this is going to go on for very long. It's not a nice thing. But nonetheless, we have to take advantage of what is going on and gain more knowledge so that in future we're able to determine and predict the path of some of these epidemics. And by so doing, we get better prepared to tackle future epidemics and to save mankind from future suffering. So what I've done is to collect data from 4 countries: Italy, Spain, France, and the UK, and tabulated them between the dates of 15th February, when most of these cases were reported, and 30th March. And looking at this data, we find that on 15th February, actually there were very few cases that time. In fact, more cases have been reported in France than in Italy, and Spain, and the UK. But going forward, it looks like the cases in Italy started climbing quite rapidly compared to France, Spain, and the UK. In fact, it took quite a long time for Spain to register any cases, coming almost 11 days later, or 9 days later actually, on 24th of February. France, which had reported more cases at the beginning, the rate of crime was quite slow compared to what was happening in Italy. And in fact, when the cases started being reported significantly in Spain, they also climbed quite rapidly. UK was even slower in taking off and also in the crime, so that by 30th March, you can see the number of cases that had been reported. But looking at this data, it looks like there was no correlation between what was happening in the 4 countries. Because you can see where this is coming quickly, this is slow in peaking, then comes quickly. This takes a very long time, although more cases were reported initially. However, if you look at the data very keenly, there's something that you begin to observe. And if you look at what is happening on the 30th of March, Italy had recorded 101,000 cases, or slightly over that, and Spain had reported 63,000 cases. If you look at the time when Italy reported around the same number of cases with Spain, that is 63,000, that was happening around 23rd March. And going backwards, in fact, let's mark this in green. And going backward from this date, when the 63,000 cases have been reported, it looks like the trend then was actually comparable. At the same time, of course, if you look at the time, around 44,000 cases were reported in France. That was on 30th March. And look at the similar time when the cases were reported in other countries like Spain and also in Italy. You find that going backwards, the cases were actually comparable. So let me mark this going backwards. I just mark with blue. And then maybe from around here, we going backward, we mark in blue. And from around this one, we go mark in blue. So you can see the trend going backwards from this side and going back on this side and this side are beginning to become comparable. So actually, the trend is beginning to emerge. And even though it looked like initially there was no correlation, now the correlation is becoming clear. Again, in the UK, if you look at the point at which 20,000 cases were reported in the other countries, let's mark this in red going backwards. Sorry. 20,000 cases, maybe we could take this one. And then 20,000 cases, around 20,000. Similarly, around this time. You can see that the trend is now beginning to emerge. In fact, what it means is that in the early days, the reporting was not accurate. And therefore, when the cases became more and the reporting became better, then the actual trend now started to emerge. So, what I did is actually to correlate this data and push backwards so that what was happening on 30th of March for each of the cases is aligned to the level, the previous level, especially where what was happening in Italy, where we had comparable cases. So you can see that essentially I've just I've just pushed this back so that the 63,000 starts from here so that we can see the correlation backwards. This 44,000 goes back and starts from here, then going backwards. And therefore, what we have is the data that appears will be looking like this. There's another way to look at this. If, for example, you try to create a curve for this data, this is actually what you find. And what is happening is that if you push this curve backwards, all the way up to this point, and you push this one all the way up to where the Italy is, push this backwards, then it's likely that all these curves would fall on the same line. And you see this from this data once we have actually pushed it backwards. So this is what is going to happen. So you can see clearly that the trend is actually the same for all the countries. In fact, what it means is that the epidemic began at different times in all the countries, or started taking root different times from the 4 countries. The reason why this trend is the same up to this point is because these countries were not taking any measures. And therefore you can see that we can easily look at this trend, which is for the combined, which is coming from the combined countries, as a do-nothing case, because by that time, maybe not the keep distance was not being observed, washing of hands was not being observed. So this is actually the do-nothing curve, which is confirmed by the 4 countries. We have now seen from the data obtained from the 4 countries, Italy, Spain, France, and the UK, that the growth of the coronavirus epidemic follows the same trajectory when no measures are taken. In fact, you can take data from any of the 4 countries to represent this trajectory. So what you're going to do next is to look for a mathematical function that represents the trajectory when no measures are taken, or what we are going to call here the do-nothing trajectory. So we are saying that each of these data can be quite representative, or can very easily represent the do-nothing model. But what I'm going to do is I'm going to produce a more representative data by taking the averages of the cases that were reported on equivalent day. We call this an equivalent day because this is day 1 for France, which may not have been for Spain, which may not have been the first day specifically, but the equivalent day 1 of each of these. So here, for example, I'm going to put those averages. I'm going to start by averaging these 4 points, or these data sets average from the 4 countries, like this. And I'm going to average all the way up to the point, of course, where we have the 4 countries here. Here I'm going to average the data from the 3 countries, France, Spain, and Italy. So up to this point. And I'm going to leave out the data from Italy from day 39, because as you're going to see later, at this point, Italy had started taking measures, and this data is not fully representative of the do-nothing case. But it's going to become very useful later when we are actually demonstrating the effect of taking measures. So now the data that I'm going to use for modeling is the averages, which is more representative. Actually, we average the data from the equivalent days. This is day 1 of Italian epidemic, day 1 of Spanish epidemic, day 1 of French epidemic, and they are different. So what I'm going to do to plot the do-nothing data is I'm going to take this as the days. I'm going to put it here, and I'm going to take this data here. So you give my XY plots. And before we embark on developing the mathematical model, or getting the mathematical function that describes the do-nothing trend, we can actually infer a lot of information from the analysis of the data that we've been looking at. One of the things that we can actually infer is the time the epidemic started taking root in each of the other countries. We saw that we had to push the data from Spain by 7 days so that we could have the correlation, by 10 days in the case of France and 16 days in the case of the UK. What this tells us, it took 7 days to come from Italy to Spain. And France is just next. Geographically, France and Spain are neighboring each other. It took only 3 days to start taking root there. It took almost another week to cross the English Channel and start wreaking havoc in the UK. Most interesting, of course, UK had almost a 2 weeks lead to take care of this problem. So what I've done is to feed the data, this average data, and the number of day, one representing, of course, the X and the other one the Y, to a curve fitting software, which will give me the mathematical function that best fits the data. There are very many curve fitting softwares out there, so it's easy for you to be able to do that. The function that I found that best suits my data is given by y is equals to ax times e raised to bx. A is equals to 39.27, while b is equals to 0.1004. In other words, this function is the number of cases is equals to 39.27 times the time was on the x-axis, times e raised to 0.1004 times the time. And this is now going to be the mathematical expression that we are looking for, that fits, that best fits the data that we have obtained as a trade for the do nothing case. So what we can do is we can actually plot that function. So we call it the model do nothing, dn. So we can do that for the other numbers. And clearly you can see that from our model, for the do nothing model, the first day of the epidemic should have had 43 cases. I think in a way this is actually bringing out something that we already suspect, that initially the number of cases reported were far much lower than what was happening. So we even can now plot all these cases together and see what is coming up. So the green now is a do nothing model based on the mathematical function that we have obtained. We have seen that the do nothing projection can be represented by the mathematical function y is equals to 39.27 times t. These are the number of cases. This is the time in days. E raised to 0.1004 t. So once you get this kind of an expression, the next thing that you do is to subject it to interpretation. And I'll show you how we're going to do this. Let's look at the rate of increase of the number of cases. The rate of increase of the coronavirus cases in the do nothing projection, we have said is equals to dy over dt is equals to y into 1 over t plus 0.1004. Now, what we are saying is that if you had a certain number of cases yesterday, the following day you are going to more or less have, and this will be subject to a little bit more analysis, we'll see through all that, is the number of cases that you had yesterday multiplied by this factor. This factor is quite important, and in fact, let's look at it critically. If you look at number of days, this is t, and then we have, let's say this is 0.1, and here is 1. So, and let's say mark for 0.1004 is just around this level. 1 over t on the other side comes, if you take this to be like 10, 20, 30, 40, and 50. You can see that after 50 days, when t is equals to 50, that's after 50 days from when you start counting, 1 over t will have fallen to 0.02. So it will be somewhere like, at 10 days, it will fall to 0.1. And here it will have fallen to 0.02. So it will be like this. So you can see that initially when you start counting, this is day 1. Then this factor is more predominant in terms of determining the increase of the cases. But as you move along, you can see that the term that becomes more dominant is this 0.1004. In fact, we can see that for t is greater than, let's say 30, we can take the rate of increase dy over dt to be equal to 0.1004 y. So, in other words, we are saying that the rate of increase from, say, the previous day is just dependent on the number of cases y. It's actually directly proportional to the number of cases y. This is what we call an exponential growth. So, the exponential growth is actually defined precisely as this. The rate of increase is proportional to the number of cases. We have established that the growth of the coronavirus epidemic, when no measures are taken or the do nothing case, is given by this mathematical model dy dt is equals to y 1 over t plus 0.1004. Now, here we have taken y to represent the total number of cases that have been reported so far, including those who have healed, those who are cured, and those who are actually dead. However, we know that this dependence, or the dependence on the growth, cannot be, if there are no people who are, if let's say we had the whole population that were affected and cured, then we won't be having the spread of the disease. So it means that the dependence here must be on the active cases that have been reported. So that's the first interpretation that we have to do. The growth is dependent on the active cases. So what are the active cases? And how do we determine the active number of cases? We know that it's taking 21 days from the time you contract the disease, on average, to when you get cured. Or if you don't get cured within that period, you actually die out. So if, let's say, 21 cases, the number of cases reported today is y of t, then the number of active cases is the total cases reported today minus the total cases that were reported 21 days ago. So this is the y active. We can now modify our model to look as follows. dy over dt, that is the growth of the total number of cases, is equals to y over t minus y 21 into 1 over t plus 0.1004. So you see, now we have a modified model that is more effective of what is happening. And in fact, once we are able to plot this curve, it will be very clear to us that this kind of a trend is what we are having. The reason why the initial curve was giving us a correct projection is because there were very few cases reported. We were only dealing with very early days, so there were very few cases that were reported. And in that case, the total number of cases were actually almost equal to the active cases. So in that case, it was just as good as y, and that is why the modeling gave us such. But now, once we do our own interpretation, then we know that this is likely, or this is most likely going to be the actual trend. We have modified our model so that the rate of increase of the disease is equals to we can improve this expression if you consider certain other factors. The people who are actually going to be affected, or the people who actually can get sick, are those who have never been sick of the same disease. Because we assume that after you get sick and cured, you attain immunity. Of course, some people die. So either you have attained immunity or you have died. So we can say that those people who have already been affected and have surpassed their 21 days are not susceptible anymore to getting the disease. So the people who are susceptible to getting the disease is everybody else. If this is the total population of the country, minus those ones who have had the disease, those are the ones who are susceptible to getting the disease. And therefore the chances of getting somebody who has not gotten the disease, that is the probability of getting somebody who is not a probability, is going to be equal to P minus Y divided by the whole population, or 1 minus Y over P. So we can actually now use this factor to modify our rate of spread and finally get our model to read like dy, the rate of increase, is equals to y of t minus y 21, 1 of t plus 0.1004 times 1 minus y over t. So this is what we are going to use as a model for the do-nothing case, and subsequently I'll be able to demonstrate to you what happens when you start taking measures and decreasing this probability of getting somebody coming into contact with somebody who is affected. For the time being, we're just going to do plots and see the trends with the do-nothing case for the do-nothing case projections. This will mark the first part of the demonstration. We have been able to show you how to make a simple mathematical model to measure the growth of an epidemic when no measures are taken, or what we have called the do-nothing case. In the second part of the presentation, we will first of all apply this mathematical model to the data that has already been collected. Subsequently, we are going to show how the do-nothing case builds up if nothing is done indefinitely. Then we'll be able to show you what happens to when the measures are being taken. But for the time being, I wish to thank you for for persevering for 27 minutes to listen to this presentation. I hope it inspires you also to do the same, to do your own modeling, and also to encourage other people to do the same. The models don't replace what happens on the ground, but they are useful tools because they help us predict and they help us prepare us for what is to come next. And even in these simple models that we are making, we can still find use for them. And I'm sure if you're able to collect more data, you'll be able to come up with better models. Thank you very much.